So in the next question 2, carbonic acid is a weak acid which dissociates in two stages. So first what happened? H2CO3 mixed with water form H3O positive and HCO3. And dissociation constant for the first one is 4.17 exponent -7. Then HCO3 further dissociated and the dissociation constant is 4.79 exponent -11. So the two stages have different dissociation constants. So you have to write the dissociation constant for each. So when we write the dissociation constant for the first one, Ka1, the equation, when you check the state of the equations, this is a heterogeneous equilibria because aqueous, but water is a liquid. And we do not include the liquid or the solid in the heterogeneous equilibria. So when you write this Ka, it will be product divided by reactant, the concentration of H3O plus HCO3 minus divided by H2CO3. And for the second one, when we write again water is in a liquid state, so H3O CO3 divided by HCO3 with the concentration, but we do not include water. Why? Because the water is in a liquid state, and in heterogeneous equilibria we are not including the substance in a liquid state, only a liquid or a solid state. Aqueous state we are including, or gaseous state we include. Now, a solution of a carbonic acid with the initial concentration of 0.1 mole, which is K1 is 4.17 exponent -17. Use Ka1 to calculate the equilibrium concentration for hydrogen carbonate ion and give your answer in three significant figures. So we have the Ka, K1 is given. So we can simply work out, because if we take the first equation, so as we know, the first one, H2CO3 was dissociating into H3O plus and HCO3. I did not include water just to write. So when I write Ka, that is a product H3O positive, then HCO3 -1 divided by H2CO3. K is given for us. That's now what is our assumption here? Because we have H2CO3 dissociate into H3O plus and HCO3. So original concentration for H2CO3 was 0.1. So this was 0 and 0. At equilibrium, this will be X, this will be X, so this will be 0.1 minus X, but our assumption is that X is negligible, so we neglect that. So we have Ka, we already worked out the Ka, like the expression we worked out, and Ka value is given in the question, which is 4.17 exponent -7. So we'll substitute the value of the Ka which is 4.17 into 10 to the power minus 7. The concentration for this one is x. So this will become x squared divided by 0. 0.1. So 0.1 is divided, other side it will be multiplied. You multiply and take a square root. What's the final answer? So 4.17 into 10 to the power minus 7 multiplied by 0.1 in a square root. That will be the value for x. What's the final answer? The concentration of x is basically the concentration of hydroxonium ion and HCO3 ion. Both have the same concentrations. 2.04 exponent minus 4. So the concentration, the x value of x is 2.04 into 10 to the power minus 4. That's value of x, and that is same as the value for, because the hydrogen ion concentration and the hydrogen carbonate ion concentration will be same. In the next part, use your answer, calculate the pH. So actually we know hydrogen ion, because this H3O ion will dissociate into H plus and H2O. So we already know the concentration of H3O ion in the solution. That is same as the previous answer, like 2.04 into 10 to the power minus 3 was there. So the same amount, because the ratio is 1:1. So same amount of hydrogen ions will be there. And using the hydrogen ion, you can directly find the pH, which is equals to minus log of hydrogen ion. That's why it is of only 1 mark. The next part, state 3 assumptions you made in your calculation in B1 and B2. So last question, it was 2 assumptions. Now they're asking for 3 assumptions. So what we assume, what is our assumption? Our assumption is that the concentration of the carbonic acid H2CO3 does not dissociate or negligible change is same as at equilibrium and initial. Then what is our second assumption? We assume that no water molecule dissociate to or contribute hydrogen ions. And what's our third assumption? Because this HCO3 can also be dissociate and it will change. But when you can see, you can see this value is so small. So this one is likely to occur. HCO3 can also change. But what is our assumption? Our assumption is that because the Ka1 is higher, so it means, and Ka2 is smaller, it means negligible dissociation for HCO3 ion. Is it clear? The 3 assumptions which we made to get this answer. Now, here you can see Carbonic acid form two types of salt, carbonates and hydrogen carbonates. Solution of a sodium carbonate is titrated with hydrochloric acid. On the grid, sketch a likely shape of a titration curve. Carbonate ion required 2 moles of hydrogen ion per molecule for completely react. 10 cm cube of sodium carbonate with a concentration of 0.1 is used. The sodium carbonate solution has a pH of 11.3. 40 cm cube of hydrochloric acid was added, which is having the same concentration. pKa, it refers to like the dissociation constant, and using this dissociation constant, you can identify the vertical part. And pKa2 is 10.3. Now clearly label any equivalent point in the sketch. So they gave you the hint that there are carbonic acid because you have sodium carbonate. And this sodium carbonate forms two types of salt. What it can form carbonate, or it can form hydrogen carbonic acid, basically forming two types of salt, carbonates and hydrogen carbonate. And a solution of a sodium carbonate is titrated with hydrochloric acid. So how we will do this question? It's of 5 marks. So you have to first work out the ratios. Already it is given. That dissociation, like here, carbonate ion requires 2 moles of hydrogen ion. That's for complete. Like, so the simplest ratio, the ratio is between them is 1:2. So how much carbonic acid, how much sodium carbonate was used? Sodium carbonate is alkaline solution. And the volume of, this is the total volume of the acid which is added. So first we should start with, and this pK1 is given 6.4 and pKa2 is given 10.3. So when we start with, because first thing, the reaction, it is a reaction between a weak base and a strong acid. Why? Because the base, it's 11.3, so 11.3 is a weak base. So when you check the vertical part for a titration curve, this is a weak base and strong acid, but this is starting from, so vertical part is from 4 to 7. And in this question, we are not adding a base, we have a base and we are adding an acid. So the graph will be same, identical, but other way around. So it should be this type of graph. In which the vertical portion is from 4 to 7. And volume of hydrochloric acid, as you know, the ratio between them, like carbonate ion requires 2 moles of hydrogen ion per molecule. Like if there is one carbonate ion, you require 2 moles of hydrogen ion for a complete reaction. So identifying the vertical part, as we know, it should be from 4 to 7, because we have a weak alkali. But what about the volume? How you check the volume? At what volume? You are adding for, So what was the original volume of this sodium carbonate solution? 10 cm cube. So if I have 10 cm cube of sodium carbonate, how much hydrochloric acid should be there? It means the equivalence point will occur when 20 cm cube. So equivalence point will occur when we have 20 cm cube of. So complete neutralization. So when we add 20 cm cube and the vertical part is from 4 to 7. So the axis properly labeled. So this is 1, 2, 3, 4, 5, 6, 7. So vertical part from 4 to 7. And equivalence point and it started with 11.3. So this is 8, 9, 10, 11 and 11. So 12. So between 11 and 12, like 11.3. We identify the vertical part and we add an acid. So it will continue until the pH is about 1 or 2. And we will complete it like this. So we'll get the answer. But what happened in this question, specifically what happened in this question, if you check the original question, this will be right for a weak acid. As you can see, a weak acid for a strong base, identical type of curve will be there. But the problem, another thing is there in this question specifically, there is also pKa2, which is 10.3. Means, what does it means? There's also another reaction, as you can see. As you can see, this HCO3 ion can also dissociate into CO3 ion, which is having a Ka of 4.7 exponent minus 11. So when we complete this graph, we have to include like that the solution was having two ions. It was having HCO3 ion as well. Like the two ways the reaction will occur, because it can form hydrogen carbonate salt, it can form carbonate salt. You was having sodium carbonate was first what happened when you add this sodium carbonate to water, it will dissociate into two sodium ion and carbonate ion. So what these carbonate ions will do, carbonate ion will accept proton from the water. So as they accept proton from the water, so it will become HCO3, hydrogen carbonate, and the solution will have OH. This is one thing. Or it might accept, like from two water molecule, it might accept, so it will become H2CO3. So this can result in a formation of multiple removal of the protons from the water. And this OH has been actually neutralized. Why the solution is alkaline for the sodium carbonate? Because carbonate ion accept proton. When it accept proton, amount of hydrogen ion is less in water and amount of OH ion is more. That's why it will become alkaline solution or basic solution. And this OH is being neutralized by the HCl. So in the solution, you may have HCO3 ion or you may have CO3 ions. So both ions are possible in the solution. That is why there is another vertical part which is for pKa2, which is about 10.3. So when you complete this graph, so there should be another vertical portion at a half equivalence point. So we started, this one is 8, 9, 10, 11, and 12, 6, 5, 4, 3, 2, and 1. So vertical part from 7 to 4 for 20 cm cube, because if 10 cm cube is there, and at a half equivalence point when half of the molecules are neutralized, so at 10 cm cube there will be a small vertical part. It's up to you. You can make for 2 dots or for 3 dots. So one vertical part and the second vertical part, and so on. That is when completely sodium carbonate is reacted with 2 moles of HCl. And this is when half of the sodium carbonate is reacted with hydrochloric acid. Is it clear? How I work out the volume as well, the half equivalence point? Any doubt in this? That's why in the question they give you a hint here that pKa1 and pKa2, dissociation constant for acid 1, the pKa1, the power of dissociation constant is 6.4. So there will be one change for 6.4 and another change will be there around 10.3. Yeah, the second one, it is it's only a small amount or small quantity, so you can make for 1 or 2 dots, like a small change in pH in that part. And you can identify that dissociation constant is 10 point when the pH and pKa are same. So this is a hint that at 10.3 you should draw this vertical part or vertical portion. Then propanoic acid is a weak Bronston-Lowry acid. Define the term acid. So definition of acid: acids are proton donors. That's a definition of acid. Acid are simply proton donors. If you say hydrogen ion donor, that's not acceptable. It should be proton donor. What is the pH of 0.1 mole solution of hydrochloric acid? How would the pH of any weak acid of same concentration differ from? So where pH, basically for strong acid, our assumption is that the concentration of acid, all of the acid ionize completely. So if we have HCl, it will dissociate into H plus and Cl minus. So as it dissociate into H plus, so the original concentration of the acid is same as the final concentration of hydrogen ion. And we know the hydrogen ion, so from hydrogen ion we can find the pH, which is equals to minus log of hydrogen ion. So 0.1 or 10 exponent, so I think it will be 1, the pH. So, and how the pH of a weak acid, pH of the weak acid is more than, like it will, if we compare the same concentration of weak acid, so it will have a pH more than 1 or more than 2 or more than 3, any number, but less than 7. Methanoic acid was mixed with propanoic acid. Use the data booklet to decide which of the acid is a stronger. So using a data booklet, like example, according to data booklet, the dissociation constant for methanoic acid is 1.6 into 10 to the power minus 4. And for ethanoic acid, it is 1.3 into 10 to the power minus 5. So one is, which one is a strong acid? Methanoic acid 1.6 exponent minus 4. Ethanoic acid, propanoic acid 1.3 exponent minus 5. Which one is a strong acid? So methanoic acid is a strong acid. And I told you, when you mix the two acids together, like methanoic acid mixed with propanoic acid, strong acid tend to lose proton easily. So what will be the equation for this? This will lose proton. So it will form HCOO minus, and it was H2 C2H5 COO H2 plus. That is the equation. When you mix two weak acid solutions, then one of the acid will lose proton and the other will accept proton. How you identify which one will lose? By checking their dissociation constant. The one which is having a higher value of a dissociation constant will lose proton. Calculate the pH of a solution of 0.05 mole sodium hydroxide per dm cube sodium hydroxide. Kw is given. So first thing, because sodium hydroxide, the concentration of a sodium hydroxide will be same as the concentration of sodium ion and hydroxide. Our assumption is, because strong acid ionized completely, if original concentration was 0.05, this will be 0 and 0. Then final concentration, it will be 0.05, 0.05, and this will be X. Then pH is equals to minus log of hydrogen ion. But the issue is you don't have hydrogen ion, you have hydroxide. So as we know, the dissociation constant, the Kw, is a product of hydrogen ion and hydroxide ion. At 25 degrees centigrade, this product is 1 exponent minus 14. Hydrogen ion concentration you don't know, but hydroxide concentration is 0.05. So using this, you will get hydrogen ion. From hydrogen ion, when you substitute, you will get the pH, which is equals to minus log of hydrogen ion. This is how we find the pH of strong base. Now, a buffer solution was made. We made a buffer solution by mixing 20 cm cube of 0.05 sodium hydroxide and 20 cm cube of 0.05 propanoic acid. Write an equation for this reaction. So first we have to complete the equation. So how to complete the equation for reaction between sodium hydroxide and propanoic acid? So acids are proton donors. So propanoic acid CH3, CH3, CH2, COH. Propanoic acid reacted with sodium hydroxide. So sodium will take position of hydrogen. This will be CH3, CH2, COONA plus H2. Now this is the equation. We need a buffer for, and refer your data booklet where it needed, like how you'll use a data booklet, because you need a Ka for propanoic acid. That's why you need a data booklet. So first, because this is a reaction between acid and alkali, so or making a buffer solution. So for buffer solution, Ka is equals to hydrogen ion concentration, the salt concentration divided by the acid concentration. So Ka, because of propanoic acid, so we'll use a dissociation constant of a propanoic acid. Already I mentioned in the beginning that dissociation constant, because when we are comparing propanoic acid with ethanoic acid, so propanoic acid is having a K of 1.3 exponent minus 5. And this is by data booklet, you don't have to memorize. So it's 1.3 into 10 to the power minus 5, that's Ka. So we have Ka. But what's the concentration of the salt? Basically what happened, because you mix sodium hydroxide with propanoic acid, so sodium hydroxide and propanoic acid will react with each other and it will form sodium propanoate. The ratio between sodium hydroxide and propanoic acid is 1:1. This will result in a formation of sodium propanoate, CH3, CH2, CONA plus H2. So we use 20 cm cube of 0.05 mole per dm cube sodium hydroxide, and we mix with 20 cm cube of 0.25, this part 0.25 mole per dm cube of propanoic acid. So as you can see, the formation of weak acid and its salt, this is 0.05, so it is obvious acid is in excess, so we'll have acid and we will have the formed salt. So first I will find how many moles. I can work out first how many moles will react. For sodium hydroxide, all the moles will react. So it is a limiting reagent. So first when I find the moles, I will multiply volume with concentration, but volume is in cm cube, so I should convert into dm cube. So 20 multiplied by divide by 1000 into 0.05. 20 multiplied by 0.05 divided by 1000. What's the answer? How many moles of sodium hydroxide are there? One exponent minus 3. 1 exponent minus 3 means 0.001. These are the moles of sodium hydroxide. How many moles of propanoic acid are there? It will be 20 multiplied by 0.25 divided by 1000. So that will be 0.05. Yeah, 0.005 will be there. So simplest ratio is 1:1. If 1:1 is there, this mole will be used up. How many we are left with? How many moles of acid will be left? 0.004 will be left, because the ratio is 1:1. If limiting reagent is 0.001, how many moles of propanoic acid will be there? 0.004 after the reaction. And how many moles of salt will be formed? Because sodium hydroxide is a limiting, ratio is 1:1. So same number of moles of salt will be there, 0.001. But we need a concentration because we want to substitute concentration. Now, what will be the volume? Because we take 20 cm cube, 20 cm. So these are the moles. Now we need a new concentration for salt. Concentration, the moles 0.001 divided by volume. But now the volume of solution is 20 cm cube of acid was mixed with alkali, 20 cm cube of alkali. So volume will be 40, but it will be 40 divided by 1000 because in dm cube. What's the concentration now? 0. So 0.025. And for concentration of acid, that's the concentration of acid, the moles which we have 0.004 divided by again 40. Why I'm taking 40? Because the total volume of a solution is 40. What's the answer? 0.004 divided by 40 divided by 1000. 0.1. So that's 0.1. And we have Ka. So we just solve this equation to get hydrogen ion. 1.3 into 10 to the power minus 3 is equals to hydrogen ion. The concentration of the salt was 0.025. The concentration of acid was 0.1. So 1.3 into 10 to the power minus 3 multiplied by 0.1 divided by 0.025. What is the hydrogen ion concentration? What's the hydrogen ion concentration now? 1.3 exponent minus 3 multiplied 0.1 divided by 0.025. 5.2 exponent minus 3. And take a log of this. That is hydrogen ion concentration. But you need a pH. pH is equals to minus log of hydrogen ion. Can you check the hydrogen ion value again? It is 1.3 exponent minus 5, not minus 3, minus 5 actually. So it will be 5.2 exponent minus 5. It was not, here it's minus 5. I wrote minus 3, look. So what's the pH now? When you take the pH of 5.2 exponent minus 5, like the log of 5.2 exponent 4.28. Okay. So the pH of this solution is equals to 4.28. This is how we find the pH of a buffer solution. Explain how this solution will act as a buffer when small. So again, the same way you will mention the answer. We have a reservoir. Always mention like excess or a reservoir of a propanoid ion, because here it's a mixture of propanoic acid and sodium propanoid. So we have a reservoir of a propanoid ion. Adding an alkali reduce the amount of hydrogen ion, which change the constant amount of, which increase the amount of propanoid ion, but already it is in excess. So small change hardly change the ratio of salt to acid. Is it clear? The last part, the same way you will mention. Like adding an alkali does not change the ratio between salt and acid, because we already have excess or reservoir of the salt. So overall pH will not change when small quantity is added. Not large or bulk, only small quantity. Any doubt related to the class? So I'll end the session and share the recording with you. And next week we will start organic chemistry.